Hello, hello, everyone, and welcome to tonight's Organic Chemistry Pre-Finals Review session on how to choose between SN1, SN2, E1, and E2 reactions. This is a topic I had many requests to cover, and it's actually a topic I'm quite excited to teach, so I'm happy that you're here to join me. Let me know where in the world, where in the country, where you're tuning in from. Also, let me know when is your Orgo final exam. I know quite a few students have already tested, and other students are testing as soon as tomorrow or next week. So let me know where you're coming in from. Actually, let's do a sound check. But if you hear me, if you hear my questions, then I guess that will be the sound check. So let me know in the comments. It looks like there's a bit of a delay here. So let's see. Question. Are you going to talk about SN1, SN2? I'm not going to cover the E1CB, but I will cover how to choose between SN1, SN2, E1, and E2. All right, what do we got here? Chicago 5:15. You still have quite a bit of time. Tomorrow, oh my goodness, so this will be a good pre-finals review. Virginia, and when are you, oh, I see that was tomorrow in Virginia. Basir in New York City. So we are almost neighbors. I'm in Long Island, so just about 45 minutes out of the city, testing on the 19th. Crystal, all the way from Puerto Rico. Nice. Omer is here all the way from Iraq. And I assume that emoji is how you feel about your final. So what kind of semester do you have in Iraq? Because I know that most of my students in the US have finals going on now. But I know that students in other countries follow different systems. So I'm curious when you are testing. All right. If you are ready, a couple more comments are coming in. Already took it and got a max grade. Well, first of all, hello all the way from New York to Kosovo. Congratulations. That makes me so happy. Thank you for popping in to share that. And Hadriana from California is testing on the 8th, so you have a little bit more than a week to go. Excellent. Let me know quickly, Orgo 1 or Orgo 2. And yes, this topic is required for both. In Organic Chemistry 1, this is one of your big, scary ones. And Organic Chemistry 2, this is a foundation that you have to know for your bigger picture synthesis, because you may have to put a halogen with a radical, halogenation, and then do something to it so that you can get your carboxylic acid, your enolate, your aromatic ring, and all that good stuff. Medina from New Jersey, just across the water. And I see Orgo 1, Orgo 1, Orgo 1. Yeah, I figured we'd have a lot of answers. So what say we jump right in, put a fire emoji in the comments if you are ready. And Crystal is here for the MCAT. Is that okay? So the MCAT actually tests this very often. You're not going to see crazy in-depth questions on this, but you definitely have to know how to differentiate them. If you have this, or SN1, if you have that, E2. So definitely a good topic for the MCAT. All right, where are I have a list of things I usually go through before I begin, and I totally forgot. We are going to cover a lot today, so I don't want you to worry either about copying everything down. Instead, just comment live notes, and as soon as I'm done, I will send you an email with a PDF copy of everything that you see me drawing today. So all you have to focus on is participation, asking questions, answering questions, and getting the absolute most out of this session. I also have some more practice for you, which I will talk about after. So make sure you have your questions ready to go, your fingers ready to type. And Aisha, finally call your time you're alive. Wow, yeah, it is some crazy hour in the morning for you, right? So I'm glad you popped in. It is nice to see you, well, not in person, but close enough. Medina, we are going to cover exactly that, so you're in the right place. You are very welcome, and shortcuts are my favorite. Any shortcuts that I can think of today, I will make sure to share with you. So fire emoji in the comments if you are ready to go. And we can talk about what I have on the screen here. 1 a.m. in the UK. Ouch. Again, you don't have to worry about writing everything down. Just put live notes in the comments and I will send you a PDF. Before we jump in, actually, no, we are going to jump in. In the previous chapters, you learned a reaction, you knew how to get there, you learned a product. Suddenly, we're looking at a situation where I can give you a molecule like this, and with just a slight change in conditions, I can get a pi bond or some kind of group or a pi bond in a completely different place on the molecule. And what you have to know for your final exam and what I'm going to show you today is how to quickly and easily recognize which reaction is going to take place depending on a couple of simple situations with no crazy worksheets. Not worksheets. I'm going to give you a worksheet. With no crazy flowcharts or crazy memorization, I'm going to teach you how to understand this logically. And in order to do so, we have to take a step back and start from the very beginning with the 4-part checklist. So first, I want you to let me know if instead of memorizing a crazy flowchart that tends to change depending on your professor's mood and if it's the sun is shining outside, do you think it will be easier to simply memorize the following? And let's put this in a color that stands out because we are going to use this a lot tonight. Number 1, alkyl chain. Number 2, attacker. Number 3, solvent. And number 4, leaving group. This is all I'm going to ask you to memorize. And the rest of today is going to be how to understand, how to apply this, and never, ever, ever deal with a crazy flowchart again. Well, at least not for this topic. So let's break it down piece by piece, and I'll put the checklist in the corner so that you can constantly keep an eye on all 4. And we will jump right in with the alkyl chain. When I'm looking at a molecule to determine if it will undergo SN1, SN2, E1, or E2, I'm trying to logically reason based on things that I will rule in and things that I will rule out. So the 2 carbons I'm looking at on the alkyl chain are the alpha carbon and the beta carbon. When it comes to molecules in organic chemistry, the way that we number it depends on the type of reaction we're looking at. And so for this specific class of reactions, if we have some kind of leaving group on the molecule, the carbon that is holding the leaving group, that is the alpha carbon. The carbon next to it, the second carbon, that is your beta. For students who have already started on carbonyl reactions, it's slightly different because with the carbonyl, the next one is alpha and the one after that is beta, but that's not our topic for today, so who cares? Alpha and beta, that is what we're looking for. And this is going to help us figure out a lot of the initial evaluations. What we're looking at with the alpha carbon, so first of all, the alpha is the carbon that holds the leaving group, Lg for leaving group, and the beta is the next carbon. And it doesn't have to be just one. Notice in this case, I have 2 different beta carbons and they are both beta. It just depends on what is next to it. So what are we looking at with the alpha and beta carbon? For the alpha carbon, I want to ask a couple of questions. Question 1, can it form a stable carbocation? If you think back to the mechanism for SN1 and E1, the first step is the leaving group is going to leave and a carbocation forms before we can have the next attack. And so this is a very simple yes or no question. If I cannot form a carbocation, then I cannot have an SN1 or an E1 reaction. So that'll be a good way to rule that out. So if no, that means you're going to rule out your SN1 and E1, not because you're memorizing it, but because you understand that SN1 and E1 require a carbocation. No carbocation, no one-type reaction. The second thing you're going to look for is it too sterically hindered? Is it too crowded? Because the SN2 reaction cannot happen if the leaving group is on a very crowded carbon. If it is too sterically hindered, then you have no SN2 reaction because the nucleophile cannot squeeze in there. It can't get in there to do the attack. Whoops, meant to click on that. There we go. The next carbon that we're going to look at is the beta carbon. The beta carbon next to the alpha is only relevant to the elimination reactions because with elimination, we form a pi bond between the alpha and the beta. And so this is a question a lot of students forget to look out for. Question number 1, do I have a beta carbon? But more importantly, do I have a beta hydrogen? Don't memorize this. Understand. If I don't have a beta hydrogen, I have nothing to eliminate. And if I can't eliminate, I can't do an elimination reaction. So this is a yes/no question, where if the answer is no, that means we can have no E1 or E2 because we have nowhere to form a pi bond. And the second question is if I do have a beta hydrogen and I can form a pi bond, but I can form more than one, then we want to ask which one is more substituted, because this is going to give us the more stable pi bond. And this is something we will come back to soon with Zaitsev's rule. So we're looking at the Zaitsev product. Let me explain this with a drawing to make sure that we're on the same page. If I have a molecule that looks like this, and I have chlorine as my leaving group, to grab a hydrogen and form a pi bond, I will grab either of these. So I'm just going to grab it, give it back the electrons. That is the E2 reaction. And this gives me a pi bond right here. Pretty simple, pretty straightforward. But if I have a molecule that looks like this, let's make it a little bit exaggerated. So here's my chlorine, and I have a tert-butyl group here, a tert-butyl group here. It is fully crowded. If I have a base that comes in to grab a hydrogen, there's no hydrogen here. There's no hydrogen here. There's nothing to eliminate. I have no beta hydrogen. That means I have nowhere to put a pi bond. That means I can have no E1 or E2 reaction because I have nowhere to put it. Let me know if that makes sense, if that is clear on not just this, but what to look for in general when we're looking at the alpha and beta carbon, when we're looking at the alkyl chain in reference to where we have the leaving group. Absolutely, yes, the MCAT loves to test substitution and elimination reactions. So you want to make sure that you learn easily how to tell the difference between them. So that is the first item on the checklist. Whoops, did not mean to click that. The next thing we're looking at is the attacker. So let me ask you this. Have you been worrying about how to tell the difference between a nucleophile and a base? This is one of the most common questions I get when we're going through this topic, specifically when we're looking at the attacker, the attacking nucleophile and the attacking base. Lucas, email me and I'll link you. When it comes to substitution elimination, I actually do not care about telling the difference between a nucleophile and a base. And I know this goes against everything your professor taught you because they probably spent quite a bit of time on it. Because I will counter with a question as follows. If I give you an ion, OH minus, is this a nucleophile or is this a base? Think about it. OH minus, is it a nucleophile or is it a base? And let me see a frowny emoji in the comments if this is something you've been confused about and you want to get a much, much faster way to answer it. While you're thinking about it, let's quickly define them, make sure we're on the same page. Nucleophile, and a lot of professors, for whatever reason, don't teach this, so I'm just going to go through this real quick. Nucleophile comes from nucleo, which is nucleus, and phile, which is loving. Nucleus loving. If you think of the charge of a nucleophile, nucleus is positive. Therefore, a nucleophile is something that loves positive. Well, what loves positive? Something negative or partially negative. If we look at a base, what is the definition of a base? Well, this depends on, are we looking at the Arrhenius, Bronsted-Lowry, or Lewis definition? The Arrhenius definition is an OH minus in solution. The Bronsted-Lowry definition is something that is going to give us an electron pair donor. And the Lewis definition is, well, an electron pair donor again. What is the charge of an OH minus? Negative. What is the charge or partial charge of something that has electrons to potentially give away? Well, it once again is negative or partially negative. The difference between a nucleophile and a base, well, they're kind of the same thing. So OH minus would be both. That is absolutely correct. It depends simply on the context of the situation. So to give you a real world example, I have a husband and I have a toddler. To my toddler, I am a mom. To my husband, I'm a wife. Does that make me a wife or a mom? Well, actually both. It just depends on the context of the situation. So what is the context of the situation for a reaction? Let's take a very simple starting molecule, and we'll actually use the same exact molecule, same exact situation. If I take an OH minus and I react it with this molecule right here, a chlorine on a 4-carbon chain, and the OH minus is going to choose in this situation to attack at the alpha position, kicking out the chlorine, this OH minus is acting as a nucleophile. A nucleophile is going to do a direct attack on carbon. That is how the nucleophile behaves. It attacks the partially positive carbon atom. If the OH minus instead chooses to grab one of the beta hydrogens, which it may want to do in a different situation, then in this case, if it grabs a hydrogen and collapses the electrons towards the alpha carbon, kicking out the leaving group, in this case, it is acting as a base. It is acting as a, well, depending on the solution, an Arrhenius or Bronsted-Lowry is typically the two you will have covered here, but honestly, the names don't matter. It is acting as a base. And why is that? Because it grabs a proton. Grabs a proton off the molecule. So it doesn't stay attached to the molecule the way I have in a nucleophile. Instead, it plucks a proton off. Same anion, same OH minus. The difference is in what it is doing in the reaction, and the conditions around the reaction will determine if it acts as a nucleophile or a base. And if the same molecule can act as a nucleophile or a base, why are we trying to differentiate between them if they're the exact same thing? They're not. The thing we're going to look at instead is not, is it a nucleophile or a base? The question I want you to ask instead is it a strong or a weak attacker? That is so much more important to help you determine if it's substitution or elimination, SN1, SN2, E1, or E2. So let's talk about the concept of strong or weak attacker. When we are talking about strong versus weak, what exactly are we talking about? If you joined us late, because I see more students popped in, welcome. Don't worry about copying anything that you see on the screen. Just put live notes in the comments and I will send you a PDF of everything that I am drawing. Yes, even if you're watching the recordings, I keep an eye on the comments and I will still send you the notes. So live notes in the chat and you'll get a link with how to get the PDF for this and all the other sessions that I've done. If we're looking at strong versus weak, what we're really looking at is this concept you've probably heard me say before, and that is happy, stable, unreactive. And what does that mean? If something is happy, then it is stable. It is not reactive. Think first in a real world scenario. I want you to picture this. It's the day after your orgo final. You watched this session, you watched other ones, you practiced the worksheet, you did the work, you did everything you could. You showed up to your exam and you aced it. And now it's the day after and you have no exams left. You are on break, whether it's for a day, a week, the entire summer, doesn't matter. You finally have a chance to catch up on your favorite TV show. Let me know in the comments what that is that you've been waiting to for a long time. You have your food, you have your snacks, you are set, you are good to go. You are happy. You are very, very relaxed. You are very stable. Are you getting up from the couch for anything? I don't think so. You are as unreactive as they come. Unless the house is on fire, you are not getting up, right? Unless something happens to change your situation. So let's see. Your episode just finished. There's a little commercial that they force you to sit through. You realize while this ad is going on for something you don't care about, that you're out of drink, you're out of snacks, your bladder is full, and you have to sit through this stupid commercial. You are unhappy. Your bladder is full, and you're hungry and thirsty. You are not very stable. You are now very reactive. And what is that reaction? You're going to get up and go to the bathroom, then go to the kitchen, grab more snacks, grab more drinks, become happy again, stable again. And once again, you're not moving off the couch. Think of molecules the same way. If a molecule is happy, if it is stable, it has no desire to react. And so every molecule strives to be stable. They strive to have no charge. They strive to have a full octet. They don't want to react. What makes a molecule strong or weak? If something is happy, it is weak because it does not want to react. If it is unhappy, then it is strong until it attacks something that finally makes it happy, and then it's unreactive again. What would make a molecule unhappy? It doesn't have a bladder and it's got no TV show to watch. What we're looking at is charge most of the time. Charge is a burden. And if the molecule has a burden of charge, it wants to do whatever it can to get rid of that charge. And so think of all the strong nucleophiles and the strong bases that you have studied. I've been using OH- as an example. It's got a negative charge and a tiny little atom. It can't do anything about it. But if I take that O with a negative charge, but this time I give you an acetate ion, now that charge can resonate. This is unstable. It wants to attack. This is less unstable. We're not going to call it fully stable, but this is like your bladder is half full. You could go to the bathroom. There's a commercial, so you may as well, but you could totally sit it out for a bit. Less unstable, meaning it's more stable. It's less unhappy. If I look at OH- and now compare it to a very similar molecule, which is an OH, but it doesn't have a minus, this is neutral. And if it's neutral, it's uncharged, it's got no burden, it's happy. So if I compare these two that are so similar in their atoms, this one is very reactive and this one is not very reactive. Now, if we think about the SN1, SN2, E1, E2 reactions, the main difference between an SN1 and an SN2, let's put a leaving group on here, is that if I react this in an SN2 situation, the nucleophile, comes in and attacks and kicks it out. In an SN1 situation, it has to form a carbocation first, and then the nucleophile comes and attacks. So let's understand why this is happening. If this thing is very unstable, it is very unhappy, it's not waiting around until the bromine decides, maybe, kind of, sort of, do I want to leave? Do I not want to leave? Okay, let me. It doesn't have that kind of time. Hey, bromine, gone, kick out. That's what my son says, kick out. Go gone. So it makes the nucleophile makes the leaving group go gone, in the words of my 3-year-old, and it kicks it out. So if we have something strong, it will do a direct attack. That is a 2-type reaction. If we have something weak, then it's not strong enough to kick it out. It is going to wait and wait and wait until eventually this thing is going to leave. And that is how we get a 1-type reaction. So I don't care about nucleophile versus base. I care about strong versus weak. Strong will do a 2-type reaction. Weak will do a 1-type reaction. And the same thing happens if I have a base. The base, a strong base, will grab the hydrogen and kick out the leaving group. A weak base will wait for the carbocation and then come and grab the hydrogen. So a couple of quick notes for you as you're reviewing. I'll just make it a little more organized here. Strong is a 2-type, and the key is it's fast. It's 1 step. 1 step means it's a quick reaction. Weak is going to give you a 1-type reaction. This is slow, and the key here is you have a carbocation intermediate, which is the slow and rate-determining step of the reaction. There are some exceptions, which I go through. Do I go through them in the substitution elimination series? I don't know if I do. So let me show you a couple of the exceptions here real quick. The first one is a halogen. Not fluorine, it's too small. But the remaining halogens, they make a good nucleophile, but a bad base. Halogens, especially the large ones, because they're so big, they're so stable, they're not going to pluck off a proton. But, and this is where you want to kind of picture, it's a big halogen holding charge, and the charge is just all around it. But when it comes next to something positive or partially positive, it will concentrate all that charge into one place and attack. And that's what makes it a good nucleophile. But for a base, you need to have the power to pull something off rather than attack, and the halogen is not able to do that. Just kind of an aside from this, what I'm going through today is the how-to, the logic, recognition. But the real way to master this, to make sure that you get it, is to do tons and tons of practice. And so in addition to following along with me today, I have a substitution elimination practice midterm that I created. It is not available on my website, but it is free. Just put midterm in the comments and I will give you a link to download it. That way you can take what you learned today and apply. It's quite a few pages of just substitution, elimination, and then choosing all the reactions between them. So just put midterm in the comments. I'll give you a link to download it, and then you can take all of this and practice, practice, practice. The other exception is something that is polarizable. And I kind of explained this concept already with the halogens, where it can take the charge and concentrate it in one place to attack. What else can concentrate its charge? Something that has resonance. So if you look at, I think I gave you an acetate before, right? The acetate hybrid would look something like this with a partial negative here and a partial negative here. But if you bring it next to something partially positive, then it will concentrate the charge, putting all of the negative next to whatever positive it is coming in contact with. And that way it can concentrate the charge and attack. And so if something has resonance and can polarize, it tends to be better as a nucleophile than it is as a base. On the flip side, a base exception is when we're dealing with a triple B, which stands for a big bulky base. What molecule am I referring to here specifically? Where the idea of a big bulky base is that even though it would like to do SN2, it would like to be able to attack and get attached to a molecule. The problem is it is too bulky. It's too bulky for SN2, so it is forced to do only an elimination reaction. And if we're talking about a negative big bulky base, it will be only E2 and not SN2. Tert butoxide is the one I'm referring to specifically. It's often written as T-but-O-. Sometimes you'll see it as KOTB or just a couple of different ways, but it's really just a positive spectator like a potassium and then an oxygen and a tert butyl group. Not only is this an exception in that we'll do E2 but not SN2, it will actually only give you the non-Zaitsev, so that's the Hofmann product, meaning the less substituted pi bond, even though the more substituted is more stable. So if you are not too familiar with this, make sure you go back and review the E2 reaction, but this is an exception that you absolutely want to remember. So let's go back to the checklist. Okay, and I dropped the link in the comments. Let's go back to the checklist. The next item on our list is the solvent. Now, by the time you get to the solvent, you will most likely have already solved the problem. The solvent is a formality. And Max, I have a substitution elimination midterm practice worksheet. If you put midterm in the comments, then I will give you a link to download it. It's not available on my website, but it is free. So just say midterm. I'll drop a link, and that way you can grab it and practice when we're done. For the solvent, we are looking at two types. There are three types of solvents that you will have learned: polar and nonpolar. And within the polar, you will have learned protic and aprotic. So let's break down the protic and aprotic because those are the two we're looking at. So it's polar protic versus aprotic, where A simply means without. So the question is, what is protic? What are we looking at? And to answer that, I have a question for you. Do you like to have fun? Do you like to have fun? I like to have fun. Toddler definitely likes to have fun. So does hydrogen. Hydrogen likes to have FON. Now, we're not going to see fluorine in these reactions, so it's just oxygen and nitrogen. But if you look at the periodic table, and these are the 10 atoms that I recommend memorizing for so many reasons, the trends that you have here, electronegativity up towards the right, size down to the left, you get the number so you know how many valence electrons, and so on and so on. If you look at the top of the table, nitrogen and oxygen are the two smallest highly electronegative atoms that are not so electronegative like fluorine that they're just too extreme to play with. But because of their electronegativity, if they are bound to a hydrogen atom, they are pulling and pulling. They are polar. So much of the negativity away from hydrogen, it leaves the hydrogen partially positive, so partially positive that another atom nearby is going to bond to it. The most common example that you should think of is water. Water is very, very polar. Oxygen is partially negative, hydrogens are partially positive. And so if I bring another water molecule nearby, there's going to be a very, very strong intermolecular force there. This is called hydrogen bonding. And it only happens to oxygen and nitrogen holding a hydrogen. So when we have a polar protic solvent, the solution has so much partial charge in it that it will stabilize any other charges in solution. So a polar protic solvent is anything that has hydrogen on oxygen or nitrogen. So for example, water, alcohol, ammonia, an amine, but be very careful if you have a primary amine, that's NH2. A secondary amine is HNR2, but not a tertiary amine. A tertiary amine does not have hydrogen. A tertiary amine is NRRR. Look at that. Whoops, that's not an R. No hydrogen, and therefore it does not count as a polar protic solvent. So these are going to be very, very good at stabilizing charge. And because they stabilize charge, they are going to favor SN1, not SN2, sorry, SN1, E1, and E2, but not SN2. SN2 does not like a polar protic solvent. On the flip side, if we have a polar aprotic solvent, that is when the solvent is still polar, but it is aprotic, where the A means without, and protic is hydrogen bonding. If you're taking the ACS exam, let me know in the comments, because on the ACS, you actually have to memorize what these things look like. But for the rest of you, just know the general names and idea. The common aprotic solvents you should know are, let me see if I can remember, DMSO, DMF, ether, where one of the common ones you should recognize are THF, acetonitrile, and acetone. If you have to know their structures, let's see. Acetone, THF, DMF is dimethylformamide, so that is formamide, and DMSO is dimethyl sulfoxide. So the reason I drew them out, even if you don't necessarily have, and acetonitrile, even if you don't have to know them, is I want you to take a look at all these solvents. I know I kind of sketched them messy, and realize they have hydrogens. All of them have hydrogens, but not a single hydrogen is on oxygen or nitrogen. No hydrogen, no hydrogen, no hydrogen, no hydrogen, and no hydrogen. That means we have no hydrogen bonding in these solvents. That means they don't stabilize charges or partial charges, and that means this solvent is going to prefer an SN2 reaction, because SN2 needs to be unstable. It cannot have, remember we talked about how a halogen will distribute the charge and be stable. No, we need to concentrate the charge. We need to get it all grouped into one powerful attack. So we can't have that for SN2. I think the D got erased for D. Oh, wow, we lost the D. Thank you. I don't know what MSO is. Thank you for that, Basir. And hello, I see students joined late. Don't worry about copying everything down. Just put live notes in the comments, and I will give you a link to grab the notes, even if you're watching the recording. So we have our solvent. Now we have another way to differentiate. And last but not least is the leaving group. Now the thing about the leaving group is that it's just a formality. It's really a yes or no question. Yes or no. Can leaving group leave? Well, what makes a good leaving group? If the leaving group leaves, so in the morning, my husband takes my toddler to school most days of the week. And the way it works is something like that. I'll say, bye, Benji. And they both walk out the door. And 2 seconds later, he comes back in. Last one huggy. Last one kiss. Last one. And then he leaves. And then he comes back again. And he needs something like this. Child finds so many reasons to come back. He is not a good leaving group. In order to be a good leaving group, you have to leave and you have to stay gone. You can't come back. And so if I have a really unstable group, say I have something like an OH minus, and somehow by some miracle, I manage to kick it out so that I have a carbocation in solution and an OH minus in solution. That OH minus realizes it left something at home and it needs to come back. It will immediately come back and attack that carbocation. It is not going to stay gone, and that makes it a bad leaving group. So when you're looking at the leaving group, it's really a question of, can it leave on its own and be stable? Or is it going to come back and therefore not be a good leaving group? Question. So for SN2, you want a strong nucleophile, yes. In an aprotic solvent, yes. Because you don't want the solvent to interfere with the strength of the nucleophile. Yes, exactly. You don't want the solvent to stabilize it and say, it's okay. You don't have to go and attack anything now. You can just chill. No, you want the solvent to say, go, 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 attack. Can you do a flowchart? No, 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 no. We're learning exactly how not to do a flowchart. That's why we're going through the checklist. So since we've gone through all of them, let's talk through the checklist again in very quick detail. We are looking at the alkyl chain. Alpha carbon. Will it form a stable carbocation? Yes or no for SN1 and E1. Is it too hindered? Tertiary, to rule out SN2. We're looking at the beta carbon. Do I have a beta hydrogen? Which one is most stable to kick out to grab for an elimination? The attacker, is it a 1 versus a 2 type reaction? Is it strong or is it weak? Solvent, is it polar? Well, they're all going to be polar. Is it protic or is it aprotic? If it's protic, it won't like SN2. If it's aprotic, it will. And the leaving group is, will it stay gone? We're not looking for a flow chart. All we're looking for is to understand how this works and then logically reason through the question so that you're not trying to memorize things that don't make sense. Question on the carbocation. Yes, so this goes back to carbocation stability. And let's take a quick moment to look at that. Carbocation stability is forming a carbocation that will be stabilized by the things around it. And so what can stabilize a carbocation? Something that will help share that burden of charge, or what I like to call moral support. So when you learned about inductive effect and hyperconjugation and all that, it sounds good on paper when you're filling out an exam question, but logically I want it to make sense. And so I think about carbons nearby as moral support. If I have a CH3 with a carbocation, there is nothing around it to support it. It's not very stable. Slightly more stable is if I have a primary carbocation because it's got this R group here as moral support. It's kind of maybe stable. Way, way more stable than that is if I have a secondary carbocation because now it's surrounded. It's got moral support on either side. And even more stable than that is a tertiary carbocation. So if the leaving group leaves, ask yourself, what is going to be the stability? What is the substitution of the thing that is left behind? And so that is primary, secondary, and tertiary. What else can stabilize a carbocation? Resonance, sharing that burden of charge. So if I have something like this, it's primary, but this is a primary allylic carbocation with resonance. So now it's 50% on one, 50% on the other. And what is the most stable carbocation? Benzylic. Because if I have a carbocation sitting outside a benzene ring, 1 resonance, 2 resonance, 3. So a total of 4 atoms holding that charge. And this is primary. I could have secondary and tertiary as well. This is primary benzylic. And it's about as stable as a tertiary carbocation when it's primary like that. Max, yes. So let's do a quick fly through of the reactions just to show you how the checklist works in real life, but then make sure that you practice with the substitution elimination midterm worksheet, because that is when you'll really get to break it down and test yourself. So let's start with the SN1 reaction. This is a fly through. I've done 2 in-depth live streams covering these just a few weeks ago, so they're on my channel. SN1 reaction is substitution nucleophilic unimolecular, which means that it's 1 step at a time, 1 molecule reacting at a time. And so let's use something like this. I think I had something like this in the opening question. And we'll react it with, I'm going to throw in some tricks that your professors may show you on the exam, just so you know what to expect. Let's look at the checklist and see how to determine that this can, in fact, be an SN1 reaction. So when you're looking at the checklist, you want to rule out what is not the correct answer so that you're left with just the right answer. All right, so what do we have? My alkyl chain, specifically, why did I put a carbocation on there? I need a leaving group. The carbon holding the leaving group, that's my alpha carbon right there. It's a secondary carbon. And a secondary carbon doesn't tell me anything because it could do all the reactions. So I can't rule anything out. Next, I move on to the attacker. The attacker, remember we said, is a nucleophile, negative or partially negative, or a base, negative or partially negative. Well, I don't see a negative or partially negative. Let me redraw that. All I see is an H plus. Is H plus my attacker in this case? No, because H plus is an acid catalyst. It's just here to catalyze the reaction. It is not the reactant. And so what are we going to react? In a situation where you don't have a nucleophile, you only have a solvent, the solvent is also your nucleophile. This is called a solvolysis reaction and is often the case in SN1 and E1. That means my attacker is CH3OH. Solvent is the attacker. CH3OH is neutral. And if it's neutral, that means it's weak, it's slow. And if it's slow, it's going to give me a one-type reaction. Rule out SN2, rule out E2. Next, we look at the solvent. The solvent is polar protic, which if we've already determined SN1 or E1, this validates that, yes, the charges that form when chlorine leaves and gives me a carbocation, when I have things happening in the middle, the solvent will support all those charges that form and stabilize that. Absolutely correct. SN1, no, the number is how many molecules react at the same time in the rate determining step, but this is actually multiple steps. Now, we don't have time for the mechanism, but let me know shortcut in the comment if you want to see a shortcut on how to quickly come up with products when you have just so many reactions and no time to actually work through the mechanisms. Trista, I want you to hold that question and come back to it because that's a very good question. So here's the shortcut for an SN1 reaction. Once you identify that it's SN1, you cross out the leaving group, redraw the carbon skeleton exactly as you see it. And then here's the trick. We want to add the nucleophile, but first, tell yourself, when the leaving group leaves, I will have a carbocation. Is there any potential for a hydride shift, for a carbocation rearrangement? And the answer is yes. Here's the shortcut, here's the trick we're looking at. Anytime you notice a secondary carbocation near a tertiary carbon, which in this case, secondary carbocation, tertiary carbon, you will have a carbocation rearrangement in the form of a hydride shift. You don't have to do the mechanism. All you recognize is secondary near tertiary. Tertiary is where you're going to have your new carbocation. That is where your nucleophile goes. And the next part of the trick is you cross out the hydrogen and everything else gets added at that position because the hydrogen will get deprotonated in the mechanism. We don't have time for a mechanism, so we just put it in like that. This is my SN1 product. Now, if you're thinking, wait a minute, Leah, you also circled E1. Why only SN1? SN1 and E1 are always in competition unless there are extreme circumstances like no beta hydrogen or something like that. So SN1 and E1 are in competition. That means that is one product for this reaction, but you will also have the E1 product for this reaction. So let's go through E1 real quick. E1 stands for beta elimination. Once again, unimolecular. That does not mean one step. It means one at a time in the rate determining step, meaning there's one molecule in the rate determining step. And so if I take my same starting molecule, and there's nothing really to change because the same exact conditions will give me an E1 as well. H plus is my catalyst, CH3OH, secondary, weak, polar protic. We have a good leaving. Did I actually say that? I didn't. So let me go back and say we have a good leaving group. Halogens will leave goodbye, not worried about it. Yeah, that was it. And so now we know that we ruled out SN2 and E2 based on the solvolysis, weak attacker. We already did SN1, so now let's look at E1. For the E1 reaction, we are looking at the beta hydrogen. So here's the shortcut. Remove your leaving group. redraw the carbon skeleton exactly as you see it, which I'm going to draw it right here. Actually, no, in this case, it doesn't matter, so I'll just draw it right here. Redraw the carbon skeleton exactly as you see it. Recognize that this would have formed a carbocation. Look out for a potential rearrangement. And the answer here is yes, secondary carbocation near tertiary carbon. And then you look at your beta hydrogens or your beta carbons. I have one here and one here, but because of symmetry in the molecule, I only get one product. So let's change it up. Let's actually make this asymmetrical by putting a methyl group here, because I want to show you something. Now, if I put a pi bond, there's no longer symmetry. I will have to show all potential products. And so let's move this down here. Let's put another one here. And let's add that new methyl group in so you know why we have two products. The shortcut for the E1 reaction is to identify where the carbocation will form or wind up, and then draw a pi bond between alpha to beta, pi bond between alpha to beta, and these are my two products. In this case, they're exactly the same substitution, so they're going to be the same, meaning there's no major or minor product. But if something was more substituted, then yes, I would have gotten a major and a minor. Hello and welcome. We are almost done, but the recording is up on YouTube, so you'll be able to rewatch it. And then just type live notes for the session notes. I'll give you a link to download everything that we covered today. Let's jump on over to, why isn't it letting me skip the page? There we go. Let's jump on over to the SN2 reaction. SN2 stands for substitution, nucleophilic, bimolecular. Bimolecular is a one-step reaction where two molecules react at the same time. I need a checklist because I marked up the other one. I'll just clean it in a moment. Whoops, did not mean to do that. All right, so let's take a look at, well, the same starting molecule, but I did have a question on stereochemistry, so why don't we actually change it up a bit? Let's do, actually, no, we can't do that. So if I have the same molecule, but this time I made sure to show the stereochemistry, we have, what are we reacting it with? Let's go with NaOH in DMSO. All right, how do we attack this? Alkyl chain, secondary, tells us nothing. We have everything that can happen here. It's not just sterically hindered. It's not unstable for a carbocation. There's beta hydrogens. Everything is good. Let's move over to the attacker. We said a strong negative attacker would be a 2 type, but a weak attacker is a 1 type. Well, this does not seem to have a charge. So is it strong or is it weak? That's a trick question. Because anytime you see Na+, that's a positive spectator, get rid of it. It's hiding the fact that there's an OH- there. OH- is negative. It is strong. That means there is no carbocation forming. We rule out SN1 and we rule out E1. Exactly. Yes, you are on fire today. Exactly. So the attacker tells us that it is a 2-type reaction. Then we have the solvent is polar aprotic. DMSO is aprotic, which means we're going to prefer the SN2 reaction over the E2 reaction. And the leaving group is a good leaving group. It's going to leave just a formality to verify, and we're good to go. Shortcut in the comments if you don't want to do this with a mechanism, but you want to know how to get it right with stereochemistry. Redraw your carbon skeleton exactly as you see it. Get rid of the leaving group, but pay attention to stereochemistry. If your leaving group was on a wedge, then your incoming nucleophile will go on dashes. And then all you do is add your nucleophile. And there's the product for an SN2 reaction. Last but not least, let's take a look at E2. And again, what I'm showing you today is a simple reaction to apply the checklist. But the real practice will come from doing this over and over and over. So put worksheet in the comments, midterm in the comments, but I guess you should put worksheet, that works too. And I will send you the substitution and elimination midterm practice worksheet with tons and tons of practice, like 5 pages of nothing but substitution elimination to make sure that you can get really, really confident with it. Elimination, E2 is beta elimination bimolecular. 2 molecules reacting at the same time. Bimolecular. 2 at the same time, 1 step. And as I'm drawing this out, I want you to tell me how many products you think we're going to get. We'll do the same exact situation. Chlorine on a wedge, reacting with NaOH. But this time, I'm going to put it into its own conjugate solvent, H2O. Add some heat. I'll explain why in a moment. Let's take a look at the checklist. I want to clean that up. All right. Starting with the alkyl chain, secondary tells me nothing. We've already determined that in this case. If your professor gives you a secondary leaving group, they're not trying to help you. To help you, they'll give you primary or tertiary, something where you can actually rule out a reaction. No help. The attacker is Na+ positive spectator. We already said to get rid of it. OH- is strong. Rule out SN1, rule out E1. The solvent is H2O, a polar protic solvent. That means we are going to favor E2, not SN2. Leaving group is good. And then heat is another one. Heat is going to help favor E2 over SN2 if it's a 2-type reaction, but it'll also help with a 1-type reaction. The idea here is that heat will help the activation energy be reached faster. And so if the molecule has a higher activation energy, like E2, SN1, or E1, it will happen faster. Tracy, email me about the ACS alkene stuff. So now that we know what the reaction is, how many products can we get? Let's see. The shortcut for E2 is very similar to E1, except we don't look for a carbocation. All we do is draw the skeleton as we see it, get rid of the leaving group, identify all your beta carbons. I have a green one and I have a light blue one. Draw 1 skeleton for each of your beta carbons, because then you put a pi bond between alpha and the blue beta. That one's a little drunk. There we go. Another pi bond between alpha and the green beta. And that's it. Those are my 2 products. But they're not equal. If you look at the substitution for the 2, so I highlight the pi bond and see how many carbon bonds come out of it. This one is a tri-substituted pi bond, but this one here is a mono-substituted pi bond. The tri-substituted, just like the carbocation, more substituents, more stable. This is my major product, less substituents. This is my minor product. So I get 2 products, but one is going to be way more preferred, and therefore way more of the products will form this one. You are very, very welcome. I hope it helps, and make sure you try the midterm as well. Which elimination has the anti-coplanar requirement? Oh, Trista, that is a very good question, and the answer is all of them. So let me show you what happens. When you have your elimination, if this is your hydrogen and this is your leaving group, the way that the elimination works is that the orbitals will just kind of collapse into each other like a series of dominoes. So when the base comes, electrons, electrons, electrons. Do you see how they go in a perfectly straight line? One knocks into the next one, knocks into the next one, knocks into the next one. They have to be perfectly lined up. If you have your situation like this with a hydrogen and your bromine, if the base comes in and tries to grab it and kick it up, that's a U-turn. The dominoes don't just change direction. this is not going to happen. In most of these situations, it doesn't matter, because if you have a molecule that looks like this, so let's say this is the carbon chain, and you have a hydrogen here. No, let's do it like this. A hydrogen, and that's a methyl. And then over here, you have a bromine and another methyl. So for something like this, you can't grab it. But because this thing is sp3 hybridized, it can just rotate. And when it does so, what you have, this part hasn't changed. So I still have the hydrogen and I still have the CH3. But if I rotate it such that the bromine is now, over here, and then I have my methyl and then my other methyl. Now, if this thing comes from the front, the electrons go inward. So they kind of collapse in. So do you see how we made it go in a straight line? So in a situation where the molecule can rotate, it doesn't matter. So when does the issue arise? If I have a ring, and let me show it to you in a chair conformation. If I have my hydrogen over here and my bromine, actually let's do it equatorial, the bromine like this. I cannot kick out this bromine because the electrons want to go up and there is nothing here. So on a cyclic compound, the halogen has to be, the anticoplanar has to be perfectly lined up. I will have to do a ring flip. And when I do a ring flip, let me just draw it out. When I do a ring flip, this one came down, and so bromine is now over here. The hydrogen that I drew is here. That one doesn't matter, but there was a hydrogen here, like that and like that. Now I can grab this hydrogen, because then look at what happens to the electrons. Grab, down, and down. This is what you're looking for. Now, your professor is not going to be this nice. Your professor is going to ask you the question like this. Bromine, CH3, CH2, CH3. And the question is, do I eliminate towards the methyl or towards the ethyl? So let's go with NaOCH3, CH3OH. Quick checklist, which is still completely marked up because I keep not doing that, but whatever, that works. Let's go through this really quick. The leaving group is on a secondary carbon, doesn't tell me anything. Attacker is negative, strong, 2-type reaction, get rid of SN1 and E1. The solvent is polar protic, rule out E2, rule out SN2, we're going to have an E2 reaction. The way your professor wants you to solve this is to take this molecule and put it onto a chair conformation and then do a ring flip, and oh my goodness, you don't have that kind of time. So put shortcuts in the comments if you want to see how to get the correct answer once, quickly, with 0 chair conformations drawn unless you're asked for it. And I stress that because one of my students, and Annie, I know you're watching, her professor took points off because she didn't draw the chair because I taught her a shortcut, and the professor was not happy that she knew a shortcut. Do you want to see the shortcut? It is very simple. Look at how they're lined up. Do you see what is going on here? If the hydrogen and bromine are anti to each other, the 2 conditions that have to be met is they have to be trans and they have to be anti. So on the ring, just look for trans. Very, very simple. H and leaving group must be trans. And if you draw a chair conformation, you happen to do it anti, I don't care. I'm not going to waste my time. So if bromine is on a wedge and this hydrogen here is on dashes, and this hydrogen here is on a wedge, I know that the only one I can grab is this one, because if I draw it on a chair, and for homework I challenge you to do that, that is the only one I can eliminate. And so for the product, the shortcut is to draw the carbon skeleton as you see it. The carbon that is sp3 holding the hydrogen that I grab will no longer be sp3. So that goes from a wedge to a line. Don't draw your leaving group because obviously that's gone. Draw everything else on there so that ethyl was never touched. And then you draw a pi bond between your alpha and your beta like that. And how much time did I just save by not wasting time with a chair? I'm going to say 30 seconds, 5 minutes, somewhere in between. I'll take it. All right, if you have any other questions, type them in. I know this was a lot to process. And so the goal for today was not master all of substitution elimination. My goal for today was to show you a logical way for you to slowly work through substitution and elimination using the checklist so that you can logically reason your way to SN1, SN2, E1, or E2. Let me know if that was accomplished. Let me know how you feel. And then that's only step one. Make sure that you practice. Go through the midterm. Go through my pre-finals assessment. Take your time doing so much practice until this is second nature, because then it'll be second nature on your final and you will ace it. So live notes in the comments for the notes, midterm for the substitution elimination midterm practice worksheet, and final for the entire organic chemistry one, well, the sampler, organic chemistry one pre-finals assessment. I'll drop you links for all of those. And I'm debating how many more live streams to do. So if you joined late, let me know in the comments, when is your final exam? Because I know that a lot of my students are done by the end of this week. So I'm trying to decide if I'm going to do any live streams next week. Aishan, I can't believe you're already having your final on Tuesday. So Aishan has been here, I want to say, for 90% of the live streams. And I love just working along with students that I recognize. So every time it's another topic you're working on, I see you here, you ask great questions, you're learning, you're doing so well. I can't wait to hear good news from you. Francie is testing tomorrow. Good luck tomorrow. Neja, yes, absolutely. Monday. Okay, yeah, it goes up automatically. Oh, 5:15. Okay, I misread. I thought you meant like this upcoming. You have 4 exams. I hope you mean like 4 different classes, not 4 orgo exams before your final, right? Oh my goodness. You know, as much as I love this, I do not miss school. Like the pressure of just having to do all that studying in 1 week for that final. No matter how much I say to prepare in advance, I always found myself doing things in the last minute, and I don't miss that. All right, so once I disconnect, YouTube is going to keep me on here, keeps the chat open for about 10 minutes. So any questions you have, go ahead and type them in. I'll drop all the links in once more. I'll hang around in the chat while I just finish up with linking up the notes, getting everything sent to you, and that email should come within, I don't know, sometime in the next 5 to 50 minutes. And I'll put a poll up on the community over the weekend on the YouTube community space. And so let me know, help me decide if I should do a live stream next week on which topic, and I'll see. All right, take care, guys. Thank you so much, especially for the students who have been here for multiple sessions. Thank you, thank you, thank you. If you haven't yet, subscribe to my channel. Basu, remind me what your question was. I apologize, I don't remember. I'll disconnect after your question, so I'll make sure that I answer that. Actually, just go ahead and type your question again in the comments, and I'll answer afterwards in the chat. Have a good night, guys, and I'll see you soon.